Good evening, everybody. Because it's already a little bit late, it's 9 o'clock, I will start with a small quiz question. So the question is, if you see these pictures, does anybody know to what national event these pictures are related? Maybe it's only interesting to the Dutch people. Anyone an idea? Yes? Laser printers?
Laser printers modeled to bombs or something.
No, could be, but this is something different. Any other ideas? Not any? Elections in the Netherlands a few years ago. Voting machines. I will come to this later in the presentation, so no goodies for you this evening. Maybe with some other questions. A little introduction. I work for the Netherlands Forensic Institute, and that's part of the Ministry of Justice and Security and Justice. It's an agency. We are not directly working for the police or the prosecutors or courts. We are just trying to use scientific methods to find facts. And that can be, like it's in our organization profile, the NFI is neutral with respect to questions of guilt or innocence. So we can find facts against a suspect to prove the guilt of a suspect in court. As you all know, not everybody in government is about transparency. So I'm now going to talk about some cases we did in the past, so I need some legitimate my presentation. So I looked in the NFI website, and there are some interesting facts that we in the NFI organization profile say we want to operate as transparently as possible. So that's why I'm giving this presentation. Of course, we are not allowed to tell everything, especially on cases which are not finished in court. We are not allowed to talk about running investigations, because that could create problems in court. And also another thing which legitimates my presentation, I think that the NFI welcomes interest in its work from politicians, media, and competitors, and other technology people like you are. So that's the reason why I'm here this evening. The outline of this presentation, I want to give an overview of some hardware-related forensics we did in the past time, and I will start my presentation in the previous century, like in 1997. That's the post-HIP period, because on HIP I think the last overview presentation was given by some of our former colleagues at NFI. The technology which I present here, I assume that it's already known by you in the community. But some case-related things are maybe interesting. Most of our normal cases we do, especially in the hardware area where I come from, are mostly related to traditional crimes, like murder, manslaughter, maybe very serious crimes like hardware cases. And most of the times, the ICT there, so the technology, is used as in a supportive way. So a victim is shot, and on the body they found a mobile phone. And from the mobile phone, they need to find some clues, maybe leading to a suspect. That's most of our work. I'm not going to talk much about that now. I'm now talking about the other way in which ICT is used. It's more that ICT is part of crime. And for this, because this is a kind of hardware hacker event, I want to give some examples of fraud cases we've done related to hardware. So, another small question. This is, in the NFI we have a kind of cabinet of curiosities, and there are some hardware things from the old time stored. They are related to cases in the past, and this one is before my time. I started in 1996, and this was even there when I came. Anybody an idea what this is? No idea? So I assume the old community is not here. This is a SEMAFUN device. And this long time ago, we had a pager system in the Netherlands, and some clever people, they built a kind of receiver like a software-defined radio you have now. In that time, they built a receiver with 3 bands which could capture all the pager traffic in the whole of the Netherlands. And what I've understood, some of the people were arrested, and that device came from the police to the NFI, and we need to examine it. And it's still at our lab as a curiosity thing. So maybe the original creator of this device is still here around somewhere. I'm not sure, but... So let's start in 1997 with some crypto-related stuff. In that time, you had cases with Norton discrete disk encryption. It's a very old encryption system. It's using DAS. And at that time, DAS was very hard to brute force with a normal PC or computer system. So because we had cases and those cases could not be solved fast enough with our current PCs, some of our engineers decided to use FPGAs to try to fasten that process a little bit. So they came up with a kind of rack structure where they can put PCBs in. Each PCB has a Xilinx, the fastest Xilinx FPGA chip at that time. And they try to use that setup to brute force passphrases. Not completely brute force, it's a combination of software constants and hardware measures. So part of the password came from a password book, so you generate common passwords, beginnings for example, and after you have maybe a counter, and that counter is done in hardware in a very fast way. Or you can make combinations with uppercase, lowercase, digits, strange characters, and all those combinations can be run in hardware. Some results from that time, from 1997, and then maybe a year after that. One case ran 2 weeks with a password length of 16 characters with the last 4 digits. Another one was a bit, the other 2 were a bit faster because they have shorter password length. So this was not completely brute force, but a kind of passphrase in combination with brute forcing. So the guy is also here, one of our engineers who made this device. In his first presentation, he wanted to give a live demonstration. So before his presentation started, he asked the people from the NFI in the audience, please define your own passphrase, don't tell it. And we start the cracker, and at the end of the presentation, hopefully my FPGA box have found the password. Of course, it must not be a very complex password, only 8 characters. So one of our guys who's not working anymore at the laboratory, he could type in the password, and the engineer was a little bit in stress when the password was presented, because he chose not found. So that's maybe it's a common joke, but it's not very funny if you engineered an FPGA system and you see this at the end. It's not funny. So the previous century, for us, it was the age of the personal data assistant, the PDA. There were no mobile phones at that time. Everybody was using his. In Dutch, it's called a zakagenda. But PDA is a more common word for that. And we had a lot of cases with PDAs, both from victims, but also from criminals, which are using those PDAs to store all their friends. So it's interesting for the police to know all the relationships. But of course, they all use password protection to protect their PDA. And luckily in that time, the security was not very good in those devices. So most of those zakagendas, PDAs, had weaknesses. Most of them had a kind of backup protocol. So even if they were locked, you could start a backup. It's backupping over the data cable. And if you just observe all the data passing over the data cable, you could see the password passing by just in plain, or maybe a little bit coded, but not really hashes or something like that were not very used in that time. So in the lab, we did those cases a lot. But of course, if you've done a device, and maybe if you've done it twice, it's not interesting enough anymore. You want to do something new, because we got so many cases. The people at NFI at that time decided to build a box with which the police could do those cases by themselves. And the picture on the left is the second version of that box, and we called it ZERT, because the Americans had CERT, Quick Emergency Response Team, we have our ZAC Agenda emergency response team at that time. So it was just a kind of a hardware-software interface box with a kind of GUI on the right. You could select your brand and type of PDA. You connect the right cable to the ZERT box. And then, in fact, you get the key combinations you need to type to, for example, start a backup protocol. And then the ZERT box gets all the backup data and extract the password from the backup data. And then it was presented on the box on the right. You see that in this case, it's, I think, QWERTY was the password for this device. And this was used by the Dutch police, and also we give away some of these boxes to other countries, friendly nations. Of course, that's a little bit a relative thing, a friendly nation, but and they are also used in other countries to crack PDAs. Nowadays, you never see any PDAs in cases anymore. It's all mobile phones. For some cases, we had a problem because we normally in forensics we first use a reference device. So you start with your own ZAC Agenda PDA. You try to measure things. You connect a logic analyzer. You observe things, and as soon as you think you found a method to bypass the password or to find the password, then if you are sure that it's reproducible and it doesn't erase all your data, because that's not so funny in a forensic investigation, then you do it on a case. The problem is, if you have a PDA under investigation and you can't buy the reference module, you're stuck, because we are not going to experiment on a real case, because if something goes wrong, and those devices were battery backup RAM based, if you screw it, then your data is gone. So in a very small amount of cases where we don't have reference devices, what we use there is a robot. This is a picture of the robot. You see the camera in front of it, small part, and it's a kind of plotter device with a small, PDA style thing which can push buttons. And on the user interface here, you see that you can define for each specific PDA kind of sequences, like how to start up, which keys you need to push for startup, which keys you need to push for present password, and then of course you need to define all the passwords. So next screen you see such a sequence. This is, I think, the reset sequence. You need to push the time and the lock button. You can also, for each specific key, you define the X, Y, Z coordinates for the robot. If you've done that for that specific device, in the next screen you can choose the password list, for example, you want to try, or maybe you want to try only digits, and then you start a robot and it's trying all those different combinations. And the camera above it used a kind of neuro software tool which sees difference on the display, because mostly there's a difference between a right password and a wrong password in the display, because it says password wrong or okay. So the camera could automatically detect the difference, and in that way it was possible to fully automatically try different passwords. Of course, you can do it, sometimes it runs for weeks, but because it's mechanical, if you do it for weeks, the keyboard is not really made for pushing so many buttons for such a long time. So we had PDAs which had almost no buttons left at the end, but we were able to solve some cases with this tool. It's on the bottom side that you see here is a small adaptation which was made for me, because I was also experimenting with power analysis. Maybe you've heard about differential power analysis, simple power analysis. And sometimes what we use here, we measure in our reference device, we measure the power, and with this repeat count we could do, for example, 1,000 of the same sequences and measure all the power, and from the power you can learn, and sometimes you see in the power traces when a specific digit is wrong or right. So instead of brute forcing the whole passphrase or password, you can brute force only the first character, and from the power you see, oh, this character is now correct, go on to the next character. So that's about the PDA stuff. Before 2000, at the laboratory, smart cards were seen as a threat for our work, because at that time everybody was busy with smart cards, chip cards. There were a lot of chip card events, and they all told people that around after 2000 every Windows PC is full encrypted, and the encryption key is only stored in a smart card. So we thought, oh well, we need to do more on smart card technology. So I went to a lot of smart card congresses and technology events. but it never happened. Even now, you don't see many crypto products using smart cards for key storage. So all that knowledge was used for other things, like we built a small tool for the police for reading SIM cards and chip knips and chippers. Maybe you know that chip knip and chipper, that's a Dutch purse card, and it also stored some logging information of the largest transaction. So those tools were made with the knowledge built up from the smart card in smart card time. It's not used anymore because now you have commercial forensic tools for this. What we do sometimes and still do in cases is SIM repair. Maybe the Dutch people have seen that movie with Peter R. de Vries, where somebody was arrested, and he was first asked by Peter R. de Vries, that's a Dutch criminal TV reporter, and he was asking questions, and at the end the reporter said, "Now I'm going to call the police, what you did was really wrong." And what he did, he opened his phone, removed the SIM card, and started swallowing his SIM card, because all his friends were in his SIM card, and he was afraid for the police. And even he couldn't swallow it, so there was a plant somewhere, and he picked some leaves from the plant for digestion. It was a poisonous plant, but he survived. And those kind of SIM cards we sometimes get at NFI. So they try to destruct some evidence. What we then do, we try to open that SIM card. These are some pictures of a chemical setup to which, for example, fuming acid, you can remove the top layer of the card. And then you can inspect the silicon die. I have two examples here. One of the examples is a bonding wire connecting the card to the internal die, which is broken here. And this happens often when you try to crack your chip card. This can be repaired very easily. And this one is very destructive. Now the die is completely broken in two parts, and that's not easy to repair. The top one we could repair simply by using a probe station. And by a probe station you can connect needles directly onto the broken pads. So here we put a needle on, and the needle is connected to a smart card reader, and then you can read the card again. So that's a way of reading destructed SIM cards, rather destructed smart cards. Then the first real fraud case in the Netherlands related to chip cards. The first real fraud case with a lot of damage, I think. The fraud indicators for this fraud were, these are the phone cards used in public phone booth. So you don't use them anymore nowadays, but in that time, even at the hip, you had a public phone booth. It was hacked, I think, at that time, but you can use your card. The telecom operators, in 1998, they have seen some fraud indicators, like the price of second-hand phone cards were increasing. Apparently there are people collecting empty phone cards for their print, and the price was rising. That's strange. And was an interchange between German and Dutch cards, and they also see in the intermediate payments there was some strange rise of the intermediate payments, like there was some money created somewhere. So first we got some cards, only cards which seemed to be reloaded in some way. And we did some investigations on those cards. And later on, the police, they also did some actions to buy those devices, because there was a market where you could buy reloading boxes for empty phone cards. And the police was able to buy some of these boxes. And we were asked to investigate those boxes to see if they work and how it works. So for me, this was the first example, a real example of a fault injection attack. And to illustrate such an attack, you see here part of that counter storing the value of the phone card. You have different bytes. It's an octal counter. This is a more significant byte, and this is a less significant byte. And in this case, the counter has value n. And if I do a decrease of this counter, what happens here, you exchange one bit here, with 8 bits here, and the value is not changing because this is more significant. So you exchange, it's like an abacus counter you have learned in school. So this is a normal counter increase. Of course, if you have an empty card, you can't increase or decrease because it's 0. What they did, with fault injection, they put disturbance onto the power and onto the clock signals of the card. And what they did, they have an empty counter with value 0, and they do a normal countdown operation. And what happens is this: you exchange 1 0 with 8 ones, because at the time the logic in the card is measuring this bit value. You put disturbances, and the card thinks there's a 1 here. So it thinks it's exchanging a 1 for 8 ones, but actually it was a 0. So now you make money if you can do this. So here are some measurements we made on the interface between those rare boxes you see in the slide before and the chip card interface. And the most, you cannot really read it, but here you see power spikes. It's, I think it's around 172 volts. And that's not the normal power supply voltage for chip cards. So by putting those spikes on specific moments in time, they could force the card to disinterpret bit values. And that's a common way. It's also in academic papers. This is presented as fault injection. But it was really an actual case where people made a lot of money by reloading empty cards and selling them as full cards. So there are millions of losses with this type of fraud. And at the end of these cases, I think there were 2 people from Dordrecht in the Netherlands arrested, and they were convicted, I think, for 1 year and 6 months prison sentence. And there was also a very big industry behind it, that there were people collecting empty cards, and there were, for example, in the big cities, there were junks sitting in a house, and their only task was putting that card in the reader, pushing a button, and then somebody give them some money or something else, and they bring the cards back. So it was a real big fraud case at that time. Some other fraud, that's an attempt to rob a bank. What you see here is a kind of remote control device. It's assembled completely by commercial off-the-shelf hardware. Like here you see a video transmitter to transmit video from your PC to a TV screen. And if you look at the scheme, this is the inside. There's a lot of commercial electronics put into a box with a lot of tape and a lot of wires connecting it. But if you look at this, the functionality of this device, what it actually do, here you have the bank PC, where not a consumer transaction takes place, but the big transactions, the interbank transactions. So that's not about some euros, but big money. What they do, they intercept the video signal. It's going to the normal screen, but it's also going to the box and to the video transmitter and transmit it to outside over a video link. And they also connect to the keyboard. So they can remote control the keyboard, and they can remote look at the screen. And with that infrared receiver, of course they need to be in close proximity, they can zoom in the video to a specific part of the screen for getting usernames or getting amounts of money. So you can imagine what you can do with this. Outside of the bank, you wait when somebody has logged in or is going to get a cup of coffee, and you put an extra transaction in with your remote keyboard, and then you can transfer money to places where it's not meant to be. And the way this was found, because it was taped under a bureau of a bank employee, but it dropped down. So it's a little bit stupid way of getting such a case. They were also caught and they got prison. I don't know how many, I don't think many years, but they were arrested. After 2000, a little bit further in time, we switched over to the mobile phones, of course, because mobile phones contain a lot of personal related data. And at that time, there were no commercial products for reading phone data. And we decided, because first we started by manually getting all the phone data out of the phone by the keyboard, but that's not really interesting work to do, pushing buttons. So we wrote some software. In that time, a lot of phones had support the AT command protocol, like you have for modems. And with the AT commands, you can also read phone book information, SMSs, that kind of stuff on a logical level. So no erased data, normal user data. So we put those commands from the ETSI specifications to a tool, and automatically you could read all that normal user data. First tool was only made internally with closed source, and then we decided to make it a little bit more modular because you've got a lot of other protocols, and we didn't have enough time to implement all the protocols. So we thought, well, why not make it open source and a very modular .NET structure with plugins, and maybe other people will also make a lot of modules, which we can use again. And also for a bit transparency that people can check our code to maybe to see errors or to help us. It was released, I think, a few years after 2000, but not many people decided to write extra modules. We got a lot of support questions with people trying to use it for specific models and asking us to add extra modules, but there were not many people in the open source community to make extra software, because it's not really interesting maybe for a normal user. It's only for forensics it's interesting. Nowadays, that's all done by commercial tools, that logical extraction. We want to extract more from mobile phones, like Mark Roelofs yesterday in his presentation mentioned. What we want to do, we want to extract directly from the chip. So we call that chip forensics. We extract data from chip. Even if the phone is not functioning, or if it's protected, we just, coming from the water, open it, clean it, and then with a rework station, and this is our new rework station. The old one is in a tent in the Gerksen village. You can use it over there. We extract all the data. You see some examples. And this is the raw image, and then you need to do the decoding. This is another example of getting the chip out of the PCB. Here we don't use desoldering because some chips cannot really against those the heating of those chips. So here it's just removed physically from the PCB, and with a kind of delayering device, which is also used in the chip industry, we delayer the whole PCB and until you are at the BGA chip level, and then we can connect this to our memory toolkit, and then we can extract all data. Small example of chip forensics, a very old example. This is a bomb threat. This is the IKEA threat in 2002. Some people put 2 bombs in IKEA markets, and in the letter, what they put there, that this was only to show they were serious. So they tell in the letter it was not really meant to do harm, these 2, only to demonstrate their technology. And there was a third one, if they don't pay, they will use the third one. I think they never visited a hacker conference like this, because this was not soldering, this was just heating something using tape. It was very poorly constructed, and even it could go off without any SMS or anything else, just by touching the device. This was very dangerous. And this is where, in that time, the military explosive people were not used to these kind of stuff. They normally are used to military things and not to homemade, bad constructed electronics. So what we did, these phones had no SIM card, so normally you cannot read them. So we removed the chips from it, we read the chip, and at the end, from the 2 phones on the crime scene attached to the bomb, these are the 2 phones, and you can see the serial numbers, the EMI codes here and here. The first one is a strange one. It's 001123456789. This is because some of the police people, they put a test SIM in. And at that time, that was a procedure. If you don't have a SIM card, just put a test SIM in, and then you have access. But on the chip level, it overrides an old IMSI. Normally, there are IMSI codes here related to SIM cards that have been in that phone. So luckily, there were more here, so we could read 3 other IMSIs, and here there were also 3 IMSIs. And from those IMSIs, you can see the country and the provider, and at the end, the subscriber. And from those traces, they could find the suspects of this crime. And at the end, they arrest people, they investigated all the mobile phones, and from all that data, and it's only the IMSI and the serial number data, you could make this kind of picture. And this picture proves, it's also used in courts, that on the bomb devices, there have been SIM cards in those devices, and those SIM cards were found on the suspects, and also on other phones of the suspect. So this is very relative good proof that those people were involved in some way with the actual bomb threat. Now about the voting thing, the quiz question. That's October 2006, when Rob Gongrijp and some other people published a report. I think some of you read that report. It's a very interesting report to read. They played chess on their Dutch voting machines. And right before the elections, the NFI was asked by the government to check some additional security features. They want to add extra physical security to prevent people opening those devices. We tested them and they all failed. They were not good enough because they were tested by the people who also invented those seals. And that's a thing you never need to do. You must not test your own security because it will always work. So during the elections, it was decided that there was a threat that some voting machines will be opened right before the elections, and somebody will maybe change the firmware in those election voting machines. So what we were asked to just during the elections have a kind of instant forensic facility if there were voting machines during the elections which were not trusted, just bring them to the laboratory and examine those devices. And we talked this not only with technical people, but also with the normal forensic guys like fingerprint, DNA, and they told us, yeah, but you want to know if the firmware is okay, but we want to find fingerprints and DNA material. So if you are going to examine those machines, you need to wear gloves, you need to wear the white anti-DNA stuff. So that's why we, at the end, were people in black or in white clothes examining voting machines. Like these people in the lab. This is during the examining in the laboratory. We have a big wall with all pictures of the different, there are 3 types of hardware configurations, and we did a lot of checks, this is one of the check forms. I don't think you can read it over here in the audience, but we check the seal numbers and the whole sealing procedure. We make pictures, we open the machine, we read all the EEPROM and the PROM chips, and we compare them with known good chips by hashing and comparing them to see if there's some difference between the normal firmware and the firmware from the examined machine. And there are some additional inspections, like if somebody tried to manipulate with the keyboard stuff or with cables or other things. So this was done for each machine which was examined during the elections. And at the end, I think we investigated 7 different voting machines, and all machines, the sealing, there was something wrong with the sealing, but there was nothing wrong with the programming or any other, there are no other fraud indicators, only some errors in the sealing. So maybe somebody tried something with it, or maybe the people who put the seals on it did not follow the procedures right. And this was used by the voting commission to, at the end, decide if the elections were really good at that time. So after chip forensics, if the device is broken, if the device is correct, we call it device forensic. If the device is broken or secured in a way, we open the device and we remove the chip. Then we call it chip forensics. If the chip is broken, we can open the chip, and then we call it silicon forensics. Or if the chip is secured in a certain way, then the only thing you can do, if you don't have any methods to bypass security or to repair from the outside, just opening it is the only resort. And this is some stuff we have for opening, like the chemical setup. For acid, we have some polishing machines. This is a machine for delayering. These are nano probes. You can put probes with a kind of PlayStation controller on a nanoscale on your silicon dies. This is a rebonding device. You can rebond chips. This is an optical microscope. You can make 3-dimensional pictures, so make all the layers visible of a chip. And this is a dual beam microscope with a focused ion beam. So what you can do with this, not only look at small structures, you can even edit on silicon. Put extra silicon or remove material, make extra connections. It's like soldering with on silicon. So a few examples. This is the opening step of a chip. This is a microcontroller where you can see the die over here. Here are some pictures with this microscope. This is a kind of security break we do for removing code protection. And this is a picture made with a our former electron microscope, and this is called voltage contrast. With an electron microscope, you can visualize data, only if it's going very slow. So here you see an example where by inspecting with an electron microscope, you see data bus and address bus data passing by. But this is only working on a very low clock speed, unfortunately. This is an example of the focused ion beam, where we add an additional pad to a silicon die and connect it here, because this was too small to put probe needles on, and then you just make your own pad. And this is large enough to put such a micro probe onto, and then you can connect it to your other devices. Small example of